Hi everyone, today we're going to study sets, and this is part 1. Let's begin with the definition of set. A set is a well-defined collection of distinct objects. Capital letters like A, B, and so on are usually given to name a set, and the objects of a set, namely elements or members, are contained inside two curly brackets separated by commas. Small letters like A, B, and so on are usually used to represent the elements of a set. If the element A is contained in the set A, then we say that the element A belongs to the set A, and we denote it by this symbol. And we read this as A is an element of set A. If the element A is not in set A, we say that A does not belong to the set A and is denoted by this symbol. And we read this as A is not an element of set A. There are ways of describing a set. The first is by listing method. By listing all the distinct elements of the set in curly brackets separated by commas, the order of elements does not matter. In here we have two examples of a set by listing method. Set A has elements 1, 3, 5, and 7. Set B has the elements A, B, and C. The second way is what we call set builder notation. By using a set builder notation, the elements are represented by using a symbol X or any other variable, followed by the properties of X as an element of the set, enclosed in curly brackets. Examples: set E has elements X, such that X is a positive even integer, X is greater than 2, and X is less than 10. If we are going to write the set E by listing method, we will have the set E equals 4, 6, and 8. Another example is set A, whose elements are variable A, such that A is a natural number. Let us write the set A by listing method, and we will have A equals, the elements are 1, 2, 3, and so on. There are some standard notations for sets. Number 1 is the set N. This is the set of natural numbers. The elements are 1, 2, 3, and so on. Second is the set of whole numbers, denoted by capital W. The elements starts from 0, followed by 1, then 2, and so on. Number 3 are the integers, denoted by Z. This is composed of the natural numbers, the 0, and the opposites of the natural numbers. Set 4 is the Q, and this is the set of rational numbers. Another set is the R, and this is the set of real numbers. Set C is the set of complex numbers. Set S with exponent plus is the set of positive elements in that set S. Next is the S with an exponent minus. This is the set of negative elements in that set S. The last here is S with exponent asterisk. This is the set of non-zero elements in the set S. Let us define more terms. The set with no elements is called empty set or null set. And this is denoted by an empty set with this symbol or a zero with a slash. A set with only one element is called singleton set. Example, this set here is a singleton set with only the numeral 5 as its element. A set A is said to be a subset of the set B if and only if every element of the set A is an element of the set B. It is denoted by the symbol A is a subset of B. Now take note that the symbol here that we use in the subset, it means the set A is a subset of or equal to the set B. Now, if the set A is not equal to the set B, then we say that A is a proper subset of the set B. That means B has at least one element more than A. And this is now denoted by this symbol. And this is read as A is a proper subset of B. Example, the set A whose elements are 2, 4, 10, and 16 is a proper subset of the set E whose elements are the variable x such that x is an even integer. So we say that A is a proper subset of E. Let's go to this theorem. For every set S, number 1, empty set is a subset of it. In symbol, this is for the empty set or the null set is a proper subset of S. Second, S is a subset of itself. In symbol, we write like this. Since S is equal to itself, we use this symbol. So we say that S is a subset of S. Today we're going to study the part 2 of sets. Let us define more terms. Two sets A and B are equal, and we write A equals B if and only if they have exactly the same elements. That is, if A and B are sets, then A and B are equal if and only if for all x, x is an element of set A if and only if x is an element of set B. In this case, we have A is a subset of B and B is a subset of A. Example, the sets A whose elements are 2, 3, 5 and the set B whose elements are 3, 5, and 2 are equal because they have the same elements. The order of the elements does not matter. Also, it does not matter if the elements are listed more than once in a set. Example, the set 2, 2, 2, 3, 3, 5 and the set 2, 3, 5 are equal. Let us now study cardinality of a set. Let S be a set. If there are exactly n distinct elements in S, we say that S is a finite set and n is the cardinality of S. It is denoted by this symbol. The S is enclosed in two bars. Example, set A has elements 2, 3, 6, and 11. Then the cardinality of A equals 4. And we can see that there are 4 elements in A. If the number of elements is not finite, then set S is called an infinite set. Examples, the cardinality of a null set equals 0 because null set has 0 elements. Second, let A be the set of all the letters in the English alphabet. Then the cardinality of set A equals 26. Number 3, let Z be the set of all integers. Then Z is an infinite set. Let us now define power set. Let S be a set. The power set of S, denoted by P of S, is the set of all subsets of S. Example, what is the power set of S whose elements are 2, 3, and 5? So the P of S equals, the first element is the null set. Second, the set 2. Next, the set 3. Next, the set 5. Next, the set 2 and 3. Next, the set 2 and 5. Next, the set 3 and 5. And the last is the set itself, 2, 3, and 5. These are the subsets of this set S. This is the power set. If a set A has n elements, then it has 2 raised to n subsets. That is, if the cardinality of A is equal to n, then the cardinality of P of A equals 2 raised to n. For the above example, we see that the cardinality of S is 3. In other words, the number of elements of S is 3. Then, the cardinality of P of S equals 2 raised to 3. And this is equal to 8. It means there are 8 subsets in the power set. 1, 2, 3, 4, 5, 6, 7, and 8. Let's discuss the Venn diagram. Sets can be represented graphically using Venn diagrams. In Venn diagram, the universal set, which contains all the objects under consideration, is represented by a rectangle. Inside the rectangle, circles or other geometrical figures are used to represent sets. Sometimes points are used to represent the particular elements of the set. The following Venn diagram represents a universal set with A and B as subsets, and A is a subset of B. Today we're going to study union and intersection of sets. Let's begin with union of sets. The union of two sets is the set of elements that belong to either of the two sets. Given two sets A and B, the union is given by the symbol. This U here is the symbol for union. So we read this as A union B. And the elements of this A union B is the variable x, such that x is an element of set A or x is an element of set B. Using Venn diagram, this is the illustration for the union of two sets. The A union B is the shaded part. We can see that the whole set A and the whole set B are shaded. We have a notes here regarding cardinality of union of sets. First, the cardinality of A union B is this formula: cardinality of A plus cardinality of B minus the cardinality of A intersect B. Number 2, the cardinality of the union of three sets. Let's say A union B union C. And the formula is this: cardinality of A plus cardinality of B plus cardinality of C minus cardinality of A intersect B minus cardinality of B intersect C minus cardinality of A intersect C plus cardinality of A intersect B intersect C. Let us see this example. If set A equals 0, 2, 7 elements and set B equals 1, 3, 7 and 12 elements, find the cardinality of A union B. First, let us write A union B. Let us write all the elements of sets A and B together. If there is repetition of elements, we will just write it only once. So the elements are 0, 1, 2, 3, 7, and 12. We say that the cardinality of A union B equals 6 because there are 6 elements in the set A union B. For the cardinality of A, this is equal to 3. There are 3 elements in the set A. The cardinality of B equals 4. There are 4 elements in the set B. The A intersect B equals 7. We can see that the element 7 is common to both A and B. So the cardinality of A intersect B equals 1. There's only one element in the set A intersect B. Now for the formula of cardinality of A union B, this is the formula. We're going to substitute the values from this column. So the cardinality of A is 3 plus cardinality of B is 4 minus cardinality of A intersect B, which is 1. So we have 3 plus 4 minus 1, total is 6. This is the final answer. Let us now discuss intersection of sets. The intersection of two sets is the set of common elements of the two sets. Given two sets A and B, the intersection is given by the symbol. This inverted U is the symbol for intersection. So we read this as A intersect B. The elements is the variable x, such that x is an element of A and x is an element of B. Using Venn diagram, this is our illustration. We have the set A and set B, and we say that the A intersect B is this shaded part. Let us see this example. If set A equals 0, 2, 7 elements, and B equals 1, 3, 7, and 12 elements, find A intersect B. We can see that the common element for A and B is that number 7. So we write it here. So this is the final answer. There is a note. If there is no common element between two sets, then the intersection is a null set. Today we're going to study disjoint sets and complement of a set. Let's begin with disjoint sets. Two sets are said to be disjoint if their intersection is the empty set. Note that if A and B are disjoint sets, then the cardinality of A union B equals cardinality of A plus cardinality of B. Remember that cardinality means the number of elements in the set. For example, we have set A equals 0, 2, and 7 elements, and set B equals 1, 3, 5, and 12 elements. We can observe that there is no common element to both sets. So if we write A intersect B, the answer is a null set or empty set. And we say that the sets A and B are disjoint sets. Let's discuss complement of a set. The complement of a set is the set of elements in the universal set that do not belong to a given set. Given set A, the complement of a set is given by the symbol A bar, and the elements of A bar is the variable x as an element of universal set, such that x is not an element of A. This A bar is also represented as A raised to C. Given this Venn diagram, the set A is here in the middle and the shaded part is the A complement. Now let's have example. Let the universal set equals the numbers from 1 to 10, and set A equals 1, 4, 7, and 10 elements. Take note that A here is a subset of the universal set. If we write now the A complement, we're going to write all the elements of the universal set that do not belong to the set A. So the elements are 2, 3, 5, 6, 8, and 9. This is the final answer. Today we're going to study difference and symmetric difference of sets. Let's begin with difference of sets. The difference, or sometimes called relative complement, of two sets is the set of elements that belong to the first set but not to the second set. Given sets A and B, the difference of two sets is A minus B, and the elements are the variable x, such that x is an element of set A and x is not an element of set B. To illustrate, we have the figures here. The sets A and B are described respectively, and the A minus B is the shaded part here. For example, let set A equals 0, 2, 3, 6, 7, and 10 elements, and set B has elements 1, 3, 7, and 12. For A minus B, the elements are all elements of set A that do not belong to set B. So the elements are 0, 2, 6, and 10. This is the final answer. Let us now discuss symmetric difference of sets. The symmetric difference of two sets is the set of elements that belong to either one or the other set, but not to both. The symbol is A delta B. The elements are the variable x, such that x is an element of A, exclusive or x is an element of B. Sometimes this A delta B is represented by the symbol A XOR B. The set builder is this. The A XOR B equals the element x such that x is an element of A union B and x is not an element of A intersect B. To illustrate, we have the sets A and B in here. The A XOR B is the shaded part. Let's see this example. Let's set A equals 0, 2, 3, 6, 7, and 10. And set B equals the elements 1, 3, 7, and 12. Let us now get the symmetric difference. So we have A delta B, or we can write that A XOR B. Let us observe that the two sets A and B have two common elements, and those are the 3 and 7 respectively. For our answer, we're going to write all the elements of A and B combined except those common elements. So the elements of A delta B equals 0, 1, 2, 6, 10, and 12. This is the final answer. Today, we're going to study Cartesian product. Let A and B B2 sets. The Cartesian product of A and B, denoted by A times B, is the set of all ordered pairs AB, where A is an element of set A and B is an element of set B. By set builder notation, it will be like this. A times B equals the ordered pair AB such that A is an element of set A and B is an element of set B. Let us see this example. Let set A has elements A and B, and set B has elements 1, 2, and 3. Find the Cartesian product of A and B. So our A times B equals the ordered pair AB such that A is an element of set A and B is an element of set B. So the answer is like this. The first element is A1, second is A2, third is A3, fourth is B1, fifth is B2, the last is B3. So we take the first element from set A and the second element coming from set B. There are notes here. Number 1, the ordered pair AB is different from the ordered pair BA. The Cartesian products A times B and B times A are not equal unless A is an empty set or B is an empty set, so that A times B equals B times A equals empty set, or it can be A equals B. So this is our final answer here. Let us define ordered n-tuple. The ordered n-tuple A sub 1, A sub 2, up to A sub n is the ordered collection that has A sub 1 as its first element, A sub 2 as its second element, and A sub n as its nth element. In connection to this, we're going to study Cartesian product of the sets A sub 1, A sub 2, A sub 3, up to A sub n on that order. The Cartesian product of the sets A sub 1, A sub 2, A sub 3, up to A sub n, denoted by A sub 1 times A sub 2 times A sub 3 times up to A sub n, is the set of ordered n-tuples A sub 1, A sub 2, A sub 3, up to A sub n, where A sub I is an element of the set A sub I, for I equals 1, 2, 3, up to n. By set builder notation, we will write like this. Let us see this example. Let set A equals A, B. Let set B equals 0, 1, and 2. And set C equals alpha. Find the Cartesian product of A, B, and C. So we have three sets here, and we write A times B times C. And the elements will be of this form: A, B, C, such that A is an element of set A, B is an element of set B, C is an element of set C. So for our Cartesian product, the elements are here. The first is A, 0, alpha. Second, A1 alpha. Third, A2 alpha. Fourth, B0 alpha. Fifth, B1 alpha. And the last, B2 alpha. This is the final answer. There is a remark here with regard to cardinality of the Cartesian product. So we read, the cardinality of a sub 1 times a sub 2 times a sub 3 times up to a sub n equals cardinality of a sub 1 times cardinality of a sub 2 times cardinality of a sub 3 times up to the cardinality of the last set, a sub n. Remember that cardinality means the number of elements in a set. In our example here, the cardinality of A times B times C equals cardinality of A times cardinality of B times cardinality of C. Putting the corresponding values, we have 2 times 3 times 1. Cardinality of A is 2, as we see that there are 2 elements in set A. Cardinality of B is 3. There are 3 elements in set B. Cardinality of C is 1. There is only 1 element in set C. So 2 times 3 times 1 equals 6. We can count the number of elements in this Cartesian product. 1, 2, 3, 4, 5, and 6. Today we're going to study set identities. Given the universal set U and the sets A, B, and C. The first identity is commutative loss. It says A union B equals B union A. Also, A intersect B equals B intersect A. Number 2, associative loss. The first is A union the operation B union C equals the operation A union B union C. Also, A intersect the operation B intersect C equals the operation A intersect B intersect C. Third is distributive loss. Number 1, A union the operation B intersect C equals the operation A union B intersect the operation A union C. Also, A intersect the operation B union C equals the operation A intersect B union the operation A intersect C. Number 4 is identity loss. It says A union a null set equals the set A. Also, A intersect the universal set equals the set A. Number 5 is complement loss. In here, there are many identities. The first is the complement of set A equals set A. Next, A union the complement of A equals the universal set, the U. Third, A intersect the complement of A equals null set. The complement of the null set equals the universal set. The complement of universal set equals the null set. Number 6 is idempotent loss. We say that A union A equals A. A intersect A equals A. Number 7 is universal bound loss. A union universal set equals universal set. A intersect a null set equals a null set. Number 8 is De Morgan's loss. The complement of the operation A union B equals the complement of A intersect the complement of B. The complement of the operation A intersect B equals the complement of A union the complement of B. Number 9 is absorption loss. A union the operation A intersect B equals A. A intersect the operation A union B equals A. Number 10 is the difference law. It says A minus B equals A intersect the complement of B. Today, we're going to study computer representation of sets. One method to represent sets using a computer is by storing elements using an arbitrary ordering of the elements of the universal set. Assume that the universal set is finite, and also that the number of elements of U is not larger than the memory size of the computer. Specify an arbitrary ordering of the elements of U. For instance, A sub 1, A sub 2, up to the A sub n. Then represent a subset A of U with a bit string of length n, where the ith bit in this string is 1 if A sub I belongs to A, and is 0 if A sub I does not belong to A. We have some notes here. Number 1, when a bit string is represented, it will be split into blocks of length 4 bits for the purpose of easy reading. Example, for a particular bit string of 6, it will be written as 101011. The blocking of 4 bits is given priority to the rightmost numbers. We can see here that there is a gap between the second and the third numbers. Number 2, the difference of two sets is displayed in the following truth table. Let A and B be 2 bit strings. For bit string A, we have 1100. For bit string B, we have 1 0 1 0. For the difference, that will be A minus B. So we have 1 minus 1 is 0, 1 minus 0 is 1, 0 minus 1 is 0, 0 minus 0 is 0. We can see here that A minus B will have the value 1 only if A value is 1 and B value is 0. Number 3, to find the bit string for the complement of a set from the bit string for that set. Change each 1 to 0 and each 0 to 1. Let us see this example. Let the universal set has elements 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And the ordering of elements of U is defined as A sub I equals I. Let us answer the following questions. Letter A. What bit strings represent the subset A of all odd integers in U? The bit string that represents the set A with elements 1, 3, 5, 7, and 9 of odd integers in U has a 1 bit in the first, third, fifth, seventh, and ninth positions. So for our answer, it will be like this: 1 0, 1 0, 1 0, 1 0, 1 0. This is the final answer. Letter B. What bit strings represent the subset B of all even integers in U? The bit string that represent the subset B with elements 2, 4, 6, 8, and 10 of even integers in U has a 1 bit in the second, fourth, sixth, eighth, and 10th positions. So the answer is here: 0 1, 0 1, 0 1, 0 1, 0 1. This is the final answer. Letter C. What bit strings represent the subset C of integers not exceeding 5 in U? The subset C corresponds to the set with elements 1, 2, 3, 4, and 5. So the answer is 1 1, 1 1 1 0, 0 0 0 0. This is the final answer. Letter D. What is the bit string for the complement of the set C? This is our set C. Now, let us write again the bit string C. For the complement, we will just change 1 by 0 and change 0 by 1. So the complement of C is 0 0 0 0 0 1 1 1 1 1. This yields the string 0 0 0 0 0 1 1 1 1 1, which corresponds to the set 6, 7, 8, 9, and 10 of the integers in U that are greater than 5. This is the final answer. Letter E. What is the bit string for the set A union C? Here are the bit string of A and C respectively. For the union, remember that this is the same with the OR operation. For A union C, we have 1 union 1 is 1. 0 union 1 is 1. 1 union 1 is 1. 0 union 1 is 1. 1 union 1 is 1. 0 union 0 is 0. 1 union 0 is 1. 0 union 0 is 0. 1 union 0 is 1. 0 union 0 is 0. This represents the set 1, 2, 3, 4, 5, 7, and 9. This is the final answer. Problem F. What is the bit string for the set B intersect C? Here are the corresponding bit strings B and C. Now, for the intersection, this is the same with our operation AND. For B intersect C, we have 0 intersect 1 is 0. 1 intersect 1 is 1. 0 intersect 1 is 0. 1 intersect 1 is 1. 0 intersect 1 is 0. 1 intersect 0 is 0. 0 intersect 0 is 0. 1 intersect 0 is 0. 0 intersect 0 is 0. 1 intersect 0 is 0. The bit string represents the set with elements 2 and 4. This is the final answer. Letter G. What is the bit string for the set A minus C? The bit strings A and C are here. For the difference, remember that the A minus C will only be 1 if A is 1 and C is 0. So we have 1 minus 1 is 0. 0 minus 1 is 0. 1 minus 1 is 0. 0 minus 1 is 0. 1 minus 1 is 0. 0 minus 0 is 0. 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 0 is 1. 0 minus 0 is 0. This bit string represents the set with elements 7 and 9. This is the final answer. Letter H. What is the bit string for the set B XOR C? The bit strings B and C are here. For the XOR, we will get a value of 1 if one of the elements is exactly 1 and the other must be 0. So B XOR C will be like this. 0 XOR 1 is 1. 1 XOR 1 is 0. 0 XOR 1 is 1. 1 XOR 1 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. 0 XOR 0 is 0. 1 XOR 0 is 1. 0 XOR 0 is 0. 1 XOR 0 is 1. This bit string represents the set 1, 3, 5, 6, 8, and 10. This is the final answer. I hope you learned something from this video. See you again next time.